All right, guys, so today we're going to take a look at how temperature affects water density. So in terms of the oceans and in terms of the currents that circulate through the oceans, density is a really important thing because denser water will sink, and then of course currents will flow downwards. Less dense water will float up towards the surface. And so a lot of things affect the density of ocean water. One thing in particular is the amount of salt in it, okay? The other thing, of course, is the temperature. And so that's kind of what our little exploration is about today. It says here, ocean water temperatures vary from equator to pole and change with depth. Temperature, like salinity, affects the density of seawater. However, the density of seawater is more sensitive to temperature fluctuations than salinity. Salinity is how much salt is in it. Cool surface water, which has a greater density than warm surface water, forms in the polar regions, sinks, and moves towards the tropics. So these are the kind of the deep underwater ocean conveyor belt currents that we talked about in our lecture. Okay, so what we're going to do here in our little exploration is we're going to take a beaker of cold tap water and with several ice cubes in it, and we're going to get it nice and cold. We're going to mix that water up, let the water get cooled down. Then we're going to fill up a graduated cylinder with the cold water that we just made in the beaker. Then the graduated cylinder, we don't want to have a bunch of ice in there or anything. We just want cold water. Then we're going to put a couple of drops of food coloring to dye some water in another test tube and put hot water in there. So we're going to heat some water to put in that test tube. And then carefully, we might use a pipette. We're going to put the contents of the hot water very carefully on top of the cold water. And yeah, because of molecular motions, there's going to be some mixing. And because we're pouring it in, there's going to be some mixing. But think about what's going to happen. You've got hot water, you've got cold water. Is the hot water going to sit on top or is it going to sink? Okay, is the cold water going to float up above the hot water or is it going to stay where it's at? Okay, so that's the question we're trying to answer here. Okay, then we're going to reverse the whole procedure. Okay, we're going to get some hot water and we're going to dye some colder water, and we're going to put the cold water on top of the hot water and see if there's any effect that happens with that. Okay, and then after we're done with that, in our observations, we're going to do a little graphing of what happens with surface temperatures and densities. Okay guys, check this out here. So I've got an experiment set up for you. We've got some cold water, which still has some ice in it. I've got some more cold water over here. It's got an ice cube in there, and I've dyed it blue for you. I have some warm water up here that I've dyed orange, and then I've got some other warm water up here that's also not dyed. So we're going to try and see what happens in these two different scenarios. The first one we're going to do with the cold water. So I'm going to take these ice cubes out of here so they're out of the way. And hold on 1 second. Okay, my ice cube's out. And now, what I want you to focus on is watch what happens as I take some of this warm water, okay, and I'm going to put a little drops of it into this beaker. Watch the top of the surface there. Watch what happens. See how it just sits on the top? Now watch what happens when one goes a little deeper. It rises right back up there to the top. I'm going to shoot this one down a little deeper too. There we go, there's a good deeper one. Goes right back up to the top. Try and get a little deeper. So that's a good one. Oh, it's gonna go right back up to the top. Had a lot in there that time. So now what you can see is that this stuff is all floating on the surface. So hot water has a lower density than cold water. So as we put the hot water in, might be cooling off a little bit now. You can see that it just rises right back up to the top. And that's how some of those deep ocean currents work. The colder water is sinking. So let's try this in reverse. Set my hot over there, or my cold with my hot on top. Now we're going to do the reverse of this. So what we're going to do is we're going to take some this is warm water, and I slide it over here a little bit so it's not sitting in the cold water puddle. Okay, so this is warm water, and we're gonna take some of our cold water that I've got here. There we go. Stir that up a little bit. And I'm gonna set the cold water on top of the hot water. So what do you think is gonna happen in this scenario? Hopefully you can see that stuff it's just descending, like immediately descending to the bottom. Pull back a little bit here. Those are no longer floating back to the top like it did in the hot water, are they? They're just dropping. Oh, look at that one, just plummeted. Get some more cold stuff again here. Right to the bottom and not back up. It's kind of fun. I could do this all day. Find a better spot on the beaker. There, that's a little better spot. You can see a little better. Boom, hit the bottom. Eventually I'm going to dye all my water blue, but you can definitely see that stuff is sinking straight to the bottom in there compared to the other water. So when you've got hot water with cold water on top, the cold water sinks downwards very rapidly. Now this is mixed up now, so it's just a little harder to tell. When you've got cold water with hot water on top, the hot water sits up top, or if it was beneath it, it would rise up. Okay, so we're gonna draw those two scenarios, or describe those two scenarios on our paper here. So just bring you over here. We're gonna go up a little bit. There we go. Okay, so in the first scenario, what we did was we took cold water, and we put the hot on top of the cold. And what happened? The hot right? The hot stays on top of the cold. It literally, when I dropped it in, it actually floated right back up to the top again. Okay, and in the reverse scenario that we did, where we took the cold water and dropped it on top of the hot water, the cold water sinks. When we add it to the warm, the cold sunk right to the bottom, and you guys saw that perfectly. Okay, we're gonna do the graph now. Okay guys, it's time to set up our graph here. This is a little bit of a different type of a graph than you may have seen before. You're gonna need two different colored pencils to make this easier to read when you're done. Now, you don't have to, but it will make it easier to read. If you look at your graph, this is a triple axis graph. So on the x-axis, we have latitude. So no matter what we're plotting, it's plotted against latitude down here. Okay, on this y-axis over here, we have temperature in degrees Celsius. So all these lines here are going up by 2 degrees, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? On this side over here, we're going to graph density, so the density of the water. And what I've done is I've labeled some of the bigger lines that would also correspond to some of the temperature lines over here to make it a little bit easier, but you're gonna have to make a little bit of a guess as to where you're at here, because here we are at 1.0240, here we are at 1.0250. So these lines go in much smaller increments, and these are the lines that are spacing in between these two big lines. So from 40 to 50 here, we've got all these little divisions in between here, okay? So let's just see kind of how that plots out. Let's start with the surface temperature. And what I'm going to do is I'm going to make my temperature orange, okay? Not that it's all hot, but that I just want to be able to tell that this is orange. And I'm going to make my density blue. Not that it's cold, but it's just going to let me know that I'm looking at density and not temperature. So if I'm at 60 degrees north right here, my surface temperature is at 5. So I'm going to go, there we go, 1, 2, 3, 4, 5 would be right there. So I'm going to put a dot right there. Okay. If my surface temperature is at 13 and I'm at 40 degrees, well, 40 degrees is here, and I'm going to go up 13. So there's 10, 11, 12, 13 would be right here. See how I'm doing that? Now I'm at 24, at 20, so I'm at the 20 degrees north. 24, there's 20, 1, 2, 3, 4. Okay. 0 degrees, that's right on the equator. I'm at 27, so not surprising, it's warmer there at 0. There's the 20 line, 1, 2, 3, 4, 5, 6, 7 would be right there. Okay. 24 degrees at 20 south, 24 degrees. 20, 1, 2, 3, 4. Boom. 15 at 40 degrees. Here's 40. There's 10, so hard to see across the whole graph. 11, 12, 13, 14, 15 would be right there. Okay. And the last one here, 2 degrees at 60. Okay. Well, there's 0, 1, 2 is right there. And so now all I'm going to do is I'm going to go ahead and I'm going to connect these dots. Don't start from the 0 axis there. You're just going to connect the dots. Nice smooth line. As clean as I can get it here. It's easier for me if I turn the paper a bit. And there we have it. There's temperatures as they relate to distance north and south of the equator. So at the equator, it's hotter, right? The water's hotter, okay, the surface water. And furthest north, it's coldest at the top surface. Furthest south, it's coldest at the surface. So this is not a surprising trend at all. Like any of us could have guessed that, right? Now let's get on to graphing surface density. And I'm going to go ahead and do that in blue. So it's a little harder to see. You're going to kind of use these lines as a reference, but really we're going to these little tick marks right here, okay? And so if this is 1.0240, okay, this next line up is they go by 2, so this will be 1.0242, 243, 244, 246. 248, 250. So you can kind of see how that works out. So our first number here is 1.0258. So 1.025, and then I need an 8 here. So I'm going to go up by 2's. So that's 1, 2, 3, 4, 5, 6, 7, 8. It's going to be right on this little hash mark, which is just above this line here. So I can use that as a reference. And I am at 60 degrees north. Okay, so 60 degrees north, that's way the heck back over on this side, so these little lines are going to be helpful here. Try to follow them. Okay, and I'm just above this line right here, over here at the 60 north. Okay, kind of see that now. The next one is going to be on the 40 north. Okay, so I'm going to be on this line, but I want 1.259, okay? 1.0259. 1.029 is going to be just before this rolls over to 6, so I'm going to be halfway up to here. So there's my spot, and I want to be on 40, so I'm going to just kind of follow, try and get under the camera here. Follow that over here to the 40 line. I'm going to be right around in here. Okay, yep, and that's it. So not a lot of change there, is there? Okay, the next one, I'll probably cross these off as I go here. I'm going to get screwed up. 1.0237. 1.0237. So that means that looking at this right here, this way down here would be 1.0230, right? So let's go, we're looking for 3.7. So 1, 2, 3, 4, 5, 6, 7. So I'm going to be right here on this thing, but I want to be at the 20 north line. So there's the 20 north. So I'm going to kind of follow over between these guys here, the 20 north line. It's going to get me close enough. Okay. Next one, 1.0238. 1.0238. Well, heck, that's practically at the same spot, isn't it? So 38 would be right on this little line right here. And I'm at 0, yep, 0 degrees latitude. So not a whole lot of change here, is there? Pretty much right there, okay? 1.0241. 1.0241 is going to be halfway to that one, and I'm at the 20 south. So 20 south. That guy over there. Here we go. Okay. 1.0261. 1.024, 25, 26. We had a bit of a jump here. 261 is going to be right here. So let's take that over to the 40 south line. There we are. The last one at the 60 south is 1.0272. 1.0272 is going to be just to this line right here. We're going to go right there. Okay, and you can see how I've graphed that out there. Now we need to draw our line in here again. So let's try and draw somewhat of a curve with this, okay? Probably do a better job with a ruler, but I'm not doing too bad. We've got a pretty steep curve here, don't we? A couple of real steep curves going on. Now we can really see what that's starting to look like. Check that out. Awesome. Okay, so let's discuss what this whole thing looks like and what it kind of means a little bit, and then we'll answer the questions. So looking at this, this is the equator, and this is towards the South Pole, and this is towards the North Pole. So you know, looking at the orange line here, it gets colder when you go towards the poles, and it's hottest at the equator, right? So let's look at the density of the water, and density is going to be dependent mostly on temperature as well as salinity. So where it's coldest over here in the north, okay, the density is quite high. That means that water is going to want to sink. Okay, don't get confused because that line is up higher. That means that it has high density, which means the water wants to sink. Okay, over here on the other pole, the density, it's even higher, isn't it? And so that water wants to sink. Okay, this is the surface water that we're talking about. Okay, the differences here in the graph have something to do with ocean currents themselves and the positions of the continents and the Coriolis effect, why you end up with a little bit colder here and denser than you do here. Okay, but you can see it's just a little bit colder here, and it makes a tremendous difference in density. So the temperature of the water, big difference for density. Let's look at the equator there. At the equator, it's the least dense water because it's hot. So it wants to float up to the surface just like that orange reddish dye that I put in the little pipette and dropped it on top of the cold water. It wanted to float on top, right? So that's what we're reading from our graph. Let's go ahead and answer the questions here. So observing, what differences did you observe in the behavior, get an actual pencil, of the 2 water samples in part A, which water sample was the most dense in each experiment? Well, we can really easily say that the most dense in both experiments, no matter what, was always the cold water. The cold was always the most dense. They've been driving that point home. How does temperature affect the density of the water? Okay, let's put some relationships down here. With the temperature, higher temperatures, I'm just going to use an arrow, let's abbreviate there. Higher temperatures is going to equal density lower. So low density, high temperature. Okay, now let's do the reverse. When temperature is low, okay, density is going to be high. Do you see it? Don't let my arrows confuse you. As temperature decreases, density increases. As temperature increases, density decreases. What we refer to that as, in science, that's called an inverse relationship. So inverse just means that when one does one thing, the other value goes the other direction. Okay? So if temperature is increasing, density we know is decreasing, which means it's going to float on top. If temperature is decreasing, density is increasing, which means it's going to sink to the bottom. If 2 water samples of equal mass had equal salinities, same amount of salt, which sample would be more dense? Water sample A, which has a temperature of 25 Celsius, or water sample B, which has a temperature of 14 Celsius. Well, we don't need to look at any graphs or anything to do that, right? Which of the 2 is going to be more dense? It's going to be the colder one, right? If you disregard salt, the colder one is going to be more dense. So we can easily say the 14 degrees Celsius is going to be more dense. Why? Because it's colder, right? Describe the density and temperature characteristics of water in equatorial regions, so near the equator. Compare those characteristics to water found near the poles. So we've got the comparison right here, okay? At the equator, it's high temp, low density. At the poles, either one, it's low temp, obviously, and high density. Okay, so we're just going to write those down here. In the equatorial, which is the equator, and now near the polar regions, the temperature is low, and the inverse of that, the density, is high. Okay. What's the reason that higher average surface densities are found in the southern hemisphere? Okay. Well, it should be obvious to you at this point that in the southern hemisphere, okay, the densities are high because it's cold, right? It's cold in the southern hemisphere. So I'm going to say in south. So because the surface temperature is colder there, you're going to have higher densities. Temperature is cold, density is way the heck up here. Okay, we're not going to go ahead and write a lab report on our experience, but our simple conclusion to this entire thing is simply that Higher temperature water is less dense, and therefore it floats upwards. Okay, lower temperature water is more dense, and therefore it sinks. And as we've discussed, density is influenced much more by temperature than it even is by salinity, by saltiness. Try and put this whole thing up here for you. Okay, it's influenced even more by temperature than it is by the saltiness of the water. Okay, and we looked at our graph. I'll put that up here again too. Here's our graph where we created this whole thing, and we saw very clearly that at the equator, okay, it's really hot. Duh, right? It's hot there. And the water, because it's so hot, is not very dense, which means it's going to want to float towards the surface. Okay, it doesn't want to sink. But near the poles, it does sink because the surface water is so cold near the poles that the water has a lot of density. It's heavier stuff. It sinks down deep, and so it flows under the ocean against the bottom of the ocean all the way up by the equator before it rises up again. It makes this whole circulating pattern. Okay, so yep, the cold water sunk when we put it in the warm, and of course, if we look at this one, the hot stayed on top of the cold when we put it on top. It didn't sink. And that's your lab. You guys can go ahead and answer the questions.